Oh, and then the exam, I am hoping to have it graded for Wednesday. If not, we'll go through the solutions on Wednesday of the last exam to at least have that reviewed. You know, it's our review day, but I'll also go through that. And, you know, I prefer to have all tests graded before going through solutions. But at the very least, we will go through them. All right, so chapter 16. So chemical and phase equilibrium. We're just going to basically really get to the chemical equilibrium. We're not, unfortunately, just not going to be able to get to the phase part, okay, just because of time limitations. Okay. Oop, what just happened? All right. All right. So again, we're going to stick with the phase part, or sorry, the chemical equilibrium. So it'll be, you know, equilibrium, reacting system. We're going to look at the second law, okay, in a reacting system, because we really didn't utilize that. And it's going to be this Gibbs function, which you kind of saw in chapter 12, and you saw it a little bit again in 15 in the lecture slides. And what will come out of this, when we apply it, we'll have a chemical equilibrium constant, and we'll be able to apply it, okay? And we'll be able to apply it to simultaneous reactions. So what does that mean? When people were asking in chapter 15, how do you know, what do you put in your products, right? We had some hydrocarbon reacting, you know, with some oxygen, and it had, let's do the C and H the other way. You had some kind of hydrocarbon reacting, and we normally have just CO2, you know, if it's a stoichiometric, we had something that looked like this, right? Well, what if we wanted to put CO here, right? Now we're going to end up having too many unknowns, okay, to just be able to solve this with the balance of carbon, oxygen, and nitrogen. And that's where we can bring in an equilibrium equation to get our extra equation for that extra unknown. Okay? All right, so where does this start? Well, we're going to bring in the second law, okay? So for chemical equilibrium, we know the increase of entropy principle, okay? So if we apply it to a reacting system, let's just kind of look at the figure. If we have all our reactants, so just everything on the left side of our equation, and they start reacting, and we calculate the change in entropy, okay, as it's going through. Basically, we'll hit the top point, and for it to keep going beyond that, would be in violation. It'd basically be violating that greater than or equal sign. So right here, then, is where we have our equilibrium composition. Okay, so it's our maximum in this case. All right. All right. So now we're going to start deriving and bringing in the Gibbs part of this. Okay. So it gets complicated before it gets easier. Okay. So we have a few pages of the derivations, and then what we end up with is a nice, easy equation to work with. But to get there, we got a few derivations to apply. Okay. All right. So we're gonna first off apply. You know, this is our COE, and this change in entropy is greater than or equal to dQ over T. So if we put that together, so basically just solve for dQ here and put it in our chain conservation energy equation, and keep our greater than or equal sign, and it gets moved around, we end up with this equation. Okay, so we're going to bring that back later on. So now we start, and we go with a different one. We go with our Gibbs. Okay, so we define this Gibbs kind of quickly in chapter 12. Okay, but it's just enthalpy minus temperature times entropy. Okay, and if we just do the change, so that would make it change in Gibbs, and that would be the change in enthalpy, and then we're just having to do TdS SDT for that component right there. Okay, so we just got the differential. Well, we're going to now apply which we've done a few times, the differential for enthalpy. Okay, we did that a lot to get for the constant pressure process in that, because enthalpy is U plus PV, and our differential in enthalpy is du plus P dV plus V dP, right? So that's what you see right here, okay? And we're doing this for a constant temperature and constant pressure, so that term goes away, and this term goes away because that's change in temperature, so that goes away also, okay? So now we're just left with this, which happens to be the same thing of what we had up here, okay? So that tells us also that the Gibbs has to be less than or equal to 0, the change in Gibbs, okay, for this reacting system. Okay, so that means since this one's less than, right? When we were looking at this one, it was greater than or equal. So that means for Gibbs, we're going to be looking at the minimum value, okay? Or when it equals the change of 0, that's chemical equilibrium. So looks similar, just as the entropy change, but now we're in the different direction because that greater than or equal went to less than or equal. Okay, so now we start at reactants, right? And we work our way, and reactants start reacting, some to products, but we hit this point, and it can't go past because we would have a violation of the second law. Okay, so we're not all the way to 100% products. We're not 100% reactants. Somewhere in between, we found an equilibrium. All right, so we have that to start off with. So we know this one, and this will come back. Okay. All right, so now we got to bring in the reaction. Okay, how to apply it to a reaction. Okay, so here is just some reaction. Okay, so it has, we normally had something with, moles of something in A, moles of B, going to moles C, not a B there, and then we'd have the moles of some D. Okay, well, this is a reacting system, so the moles are changing, right? So that's why we have the change in moles here, right? Okay, so we have change in moles. So the moles are changing because they're going to equilibrium, right? All right, so we take the equation we just derived right here. So we know the change in Gibbs is equal to 0 when we are at chemical equilibrium, okay? Okay, so we'll start there. So that's where we started, okay? That means the change in Gibbs is equal to 0, so we got to apply and find out what the change in Gibbs is for this reaction, okay? So we'll sum up each of the components, A, B, C, and D, okay? So that's why we have the summation. All right, so this is total Gibbs, so we change it to lowercase Gibbs right here times the moles, okay? Because that lowercase Gibbs will be per kilomole, and we just put in our moles, okay? So we have this, and now we just get rid of the summation by putting in each of the components, okay? So now we have C, D, A, and B of our reaction, okay? So we've now figured out, basically, for the reaction, that this equation right here, okay? All right, so we have a little bit, we've gotten somewhere. We want to figure out what this moles part is now, this change in moles, okay? So for A, B, C, and D, okay? If we go to, and you'll hear this over and over again when we do when you see the examples and we do them, is the stoichiometric reaction. That's kind of what or theoretical reaction, what we've kind of done already, okay? And so if we just have this reaction right here, it has these stoichiometric coefficients right here, okay? And the best way of thinking about that is if we look at this example right here, okay? So we have this example of hydrogen, H2 going to 2H, right? Because there's one hydrogen and it's going to one H2 and it's going to 2H, right? Well, if we had instead 0.1 H2, we'd have 0.2H, right? Well, you can kind of see there's a proportionality there, right? If we started out with 1 to 2, and that's our stoichiometric coefficient, to get to these ones, you would just have a coefficient in front of it, in front of that stoichiometric, right? You just have, in this one, you'd have 0.1 in front of each of those, okay? It would just be 0.1 times 1, and then on the other side, you'd have 0.1 times 2, right? And you can do that for each of these and get that there's a proportionality coefficient like this, okay? But it still holds to that general reaction that if you have 1H2, it has to go to 2H. It splits up the hydrogen. You have to have that proportionality to it, that you have to get those kind of stoichiometric values that you result in. Okay, so if we think of this example and do it in equation form, you would have, right, so the H2, we would have kind of a 1 here, but then you'd have this proportionality coefficient in the front, which is whatever any of these are, okay? So in any of these reactions we have here, you'd have that proportionality coefficient and then the stoichiometric one, okay? But the stoichiometric always holds at 1 and 2. The proportionality constant, we could just, if we put that, each of these in here into our equation up here for the moles, right? I'm going to do lots of arrows because those are fun. Okay, what will happen is that proportionality coefficient just cancels. It's in every term, so we can just cancel it. Okay, and just get rid of it because it really doesn't matter because we're trying to make something that's equal to 0 on the right. So that means we just end up with this nice equation of that stoichiometric coefficient from the theoretical reaction and then the Gibbs value. Okay, so it would be in this one, you'd only have A and say D here, right? Because there's only one reactant, one product, so you wouldn't have a D and you wouldn't have a B, but you would have here 1 for what goes in front of the hydrogen, H2, and then 2, which goes in front of the hydrogen. Okay. All right, so one more page of big derivations here, but we've gotten to this point, okay? Now we got to figure out how to get this Gibbs value, okay? We have the proportionality. We can get those because we just set up our theoretical reaction, okay? Just like we had here for this hydrogen. We just set that up and we know what our proportionality comes. Now we got to figure out how to get the Gibbs value in this equation. And that's this next slide, okay? All right, so we first start off with the Gibbs. So our Gibbs equation. Okay, and then we're going to do it for a isothermal process, change in Gibbs. Okay, so we're changing Gibbs. So it's lowercase though. So we have change, we have our change in enthalpy, and we didn't have to do the SDT part because it's isothermal, right? So we didn't have to have that extra term for the change in Gibbs. Where you have, because since temperature's constant, we just have that, all right? All right, and it's for an ideal gas, Okay, so the other part that happens, because it's for an ideal gas, we know our change in enthalpy is Cp delta T. So that's why the change in enthalpy goes away, because again, it's isothermal. Okay, so Cp delta T goes away. So then we're just left with change in Gibbs is negative T change in entropy. Okay. All right, so now we have the term for change in Gibbs. Right, that's what we're looking for. Is we're looking for Gibbs. We have a term for change right now, but we need it with temperature. We know, right? Entropy, we can't just look that up. We have to put in something for entropy then. Okay, so that's where the next step comes in. Bring in our entropy change for an ideal gas. Okay, so we have our equation. Well, it's isothermal again, right? So that term all goes away. Okay, so we get this isothermal equation. Now we get to put this in here for delta S. Okay, and if we do that, we end up with our equation here. So that's our change in Gibbs. All right, for our isothermal process. Here's now we have change, right? I keep mentioning we have change in Gibbs, change in Gibbs. We want actual Gibbs, right? In this equation, there's no change there. Okay, so that's our next step. So to get the actual Gibbs, we take a reference Gibbs value, and that's this, at the given temperature, and then basically get our portion that's just due to pressure. Okay, and that's from this equation right here, because this is the change from a reference, and this is our change in Gibbs that we just derived, and that gets our actual Gibbs at our temperature and pressure. Okay, so one thing you'll see, and this is kind of key when you get later on, and I'll still probably get some questions on it, is you see this got, when we move this equation right here to here, this pressure 1 kind of disappeared. You only see one pressure term in this equation below it. And that's because, for simplicity, they made pressure 1 equal to 1 atmosphere. And that's very important. That means everything, when you put in your pressures into this equation that we derive later on, has to be in atmospheres. And that's to get rid of kind of P1. Pressure 1 is already 1 atmosphere, and this is the change in pressure from 1 atmosphere. So it kind of already has a unit to it. Okay, so it's kind of important to remember that. So when we put our units into any of the equations that have pressure in it here, it's got to be in atmospheres, okay, because of this simplification you see right here. All right, so now we have an equation for our Gibbs that I said we needed to get right here. So now we put that equation in for each of those terms in this equation, okay, and that's what you see here now. We just put in that Gibbs here for C, here for D, A, and B, right? Now we have what we want, and we just simplify. So we've derived our equation, and now we simplify, and we see, what we get out of it. Okay, so first thing that is happening for the simplification is we can take all these kind of reference conditions at the temperature, and put them together, and that's what you have here. This is just, if we pulled all those out, we'll just call it this capital Gibbs at that temperature. Okay, and that's what you see down here. And then what do you have left? You have this term for each, you have this one for each one, you have this one, you have this one, right? And that's what you see right here. Okay, while we can make this a little simpler to look at and combine them because it's natural logs. So if you're adding a natural log, that's multiplication. If you're subtracting, that's division. And basically, we've just combined this whole section right here and put it together as that, okay? Because of all those natural logs, we can combine it, and you have that equation. So really, the main things you'll see is this part, okay, and this part. And now we're just going to start using it, okay? It will get a little simplified from that, but that's what all these multiple pages are of derivations come from. Okay, so So then we talked about equilibrium constant. So that term is this. All that stuff you see right here, wrong way, right here inside this natural log, that's our equilibrium constant, Kp, right there, okay? That means if that is Kp, let's go back, if that is Kp, then you have this Gibbs, and if you divide that Gibbs over here by R, U, and T, and bring this over, you just have natural log of the equilibrium constant over here, and you have this Gibbs that's just a function of temperature, RU, and temperature now. And that's what you see kind of here, okay? They've rearranged and solved for the equilibrium constant on the other side of this equation. So using this term and this term, Kp is equal to that. Okay? So it's a simplified version of what we just saw in the last slide. If we set these two equal to each other, we have this equation down here, okay? All right, but we don't typically do that because we want to use that equilibrium constant, okay? So what you see here is this version of the equilibrium constant is just a function of temperature and your reaction. And you actually have lots of values for the equilibrium constant in appendices A28. They just list the equilibrium constant. We have, I don't know, 5 or 6 reactions they give you in the book in that table, and they give you the equilibrium constant at a bunch of different temperatures. So they've just basically calculated it for those reactions, and you have your equilibrium constant. Well, if you can calculate this equilibrium constant, Kp, well, then Kp is this, and it's equal to all this terms, okay? We'll make one more simplification that's easier to use. I believe you see this is all in pressures. Well, that's not as easy to use as moles, right, in a reaction. So we'll bring in the partial pressure from chapter 13 that we have that your mole fraction is Pi over P, right, the partial pressure over the total. Okay, so we want the individual pressures because that's what you see in this equation. So if we do that for each A, B, C, and D and plug this in, you're going to get this version of the equilibrium constant. That's what you see here. Okay. So you have 3 versions. We have the one with partial pressures, 1, which comes from the derivation. It's not as useful to use, but that's the one that gets us this one in the number 3, okay? 2 is the other one that's useful, okay? That's what you see used in the tables in A28, okay? The other thing on this is that change, and we'll see it in the examples, but the change in the stoichiometric coefficient is just this, okay? CD minus AB. All right, so I think there's examples now, okay? All right, so we have our equation. We're basically just going to use, we need to get the equilibrium constant, okay? So Kp, we have this reaction right here, and it's at 25 degrees Celsius, and we're going to compare it to the Kp in the table A28. Okay, so we're going to get it ourselves, and then we're going to see how good we did it, right? So if we set up, you know, I'm going to pull this out here again, just so it's not in the paragraph. All right, so we have our equation for Kp, okay, for our equilibrium constant, to get it ourselves and not just pull it from the table. All right, so that means we have temperature, right? So we have that term. Our universal gas constant, because it's Ru, we have that, okay? So we really just got to get the change in Gibbs at the reference Gibbs at that temperature, okay? So we set up our change in Gibbs. So change in Gibbs we just have products minus reactants. Okay, so we have products right here, which is just nitrogen, and then we have N2 as our reactants. Okay, and we have to get our stoichiometric coefficients, which we have basically a 1 here and a 2 here, right? And then we have to go and grab these values from the back, and that you can just grab the Gibbs at that temperature. You can just grab those in the back of the book in the same places you grab information for. Let's just see. Okay, so if we calculate this, we're going to get so we now get this value for this term. Okay, now we're going to need to get our Kp value. So they just got, so one thing you'll see is they, right here, we have it raised to the E, all right? Well, they just moved it with natural log, okay? And that's because if you look in the table, this is one other key thing in these problems, they list Kp like this. So this is how table A-28 is, okay, is they list it as natural log. So this is probably one of the most common mistakes in these problems is the values in the table are listed like this, and you usually want Kp, right? But it's listed as natural log of Kp in the table, and that's because it changes many orders of magnitude. Okay, so all right, so if we calculate the natural log of Kp, we get this value. Okay, and this is at 25 degrees Celsius, and if we compare it to the back, the back was -367. Back of the book 480 is what the back of the book has for the natural log of Kp. So to get the actual Kp, right, we take the E, and you see this, right? You see that's why, you know, if they listed it in the table as Kp, you see this is to -160, right? Well, it goes from that low to very high to +160. So it has many orders of magnitude of change. So that's why they listed in natural log. Okay, so it's easier to list in a table form. Okay, so that the other part with it being so negative in this equation, we see that there's actually no reactions going to actually take place. So it's just going to stay as N2. So for N2 to break up into 2N requires high temperatures. Okay, so above like 1800 Kelvin when we're only at, you know, like around 300 Kelvin. All right, so another example. So this was just showing you how they get the values in the table, in table A28. This example more is how to use those values that are already in the table. Okay, so we're going to use the other side of our equation. So we use this one in the first example. We're going to use this one in this example. Okay, so this is Kp. Let me rewrite this. Kp. I'm going to need more room than that. So we're going to be using this version now of the equation. Okay, so this one right here. All right, so this case, they're saying producing hydrogen by heating water vapor to high temperature. So an an alternative to electrolysis, hydrogen gas can be produced thermally in accordance with the dissociation process. So water dissociating to H2 and O2 by heating water vapor to very high temperatures. So this would be determine the percentage of water vapor that can be separated into hydrogen and oxygen, and this, as it says, it's very high temperature, so 4,000 Kelvin, so very high, right? And 10 kPa. Okay. All right. So we've set up our stoichiometric equation, so the general one. Okay, that's what they gave us. Okay, that is our stoichiometric equation. That's our, A plus B goes to C plus D. Okay, our general stoichiometric equation, right? But in equilibrium, you have some reactants left over, right? So the reaction of H2 might all stay as H2, or some of it might react into H2. So some of the water might react into H2 and oxygen, or you might be left with all water, or it goes all the way to completion, but we don't know where we end up. Okay, so that means in the actual, we have to leave water in our products also. Okay, so that's the other key part. So this is our actual. We have X moles of H2O, Y moles of hydrogen, and Z moles of oxygen. So that means we have X, Y, and Z as what we have as the result. Okay, so when we set up our first equation, our hydrogen balance, and then our second one is our oxygen balance. So for the hydrogen balance, we have 2H. So we're looking at the actual here. So we have 2 hydrogens on the left, and on the right we have 2 times X from whatever's left over of water, and then we have 2 times Y from our hydrogen. And then we do oxygen, we have 1 in the water, X from water left over, and then you have 2Z. Okay. What they're doing here and here is just putting everything in terms of X, because we have 3 unknowns right now, X, Y, and Z. So to make it simpler to solve later on, they put everything in terms of X, so then only thing that's unknown is X in the last equation. And that's why you see that. All right, so number of total moles, we have X, Y plus Z. Okay, again, they substituted Y in here and Z in here to get this also in terms of X. Okay, and that's just more, again, for later on to help with the algebra later on. Pressure, okay, again, atmosphere. So remember when we said way back here in the derivation when you guys weren't paying attention, or maybe you were, right here. So we said it's in terms of atmosphere, right? So that makes, we gotta take our pressure of 10 kPa and put it into atmosphere, okay? Okay, so that's one of the key things that's forgotten, okay? All right, so now we have, when you go back to this equation that I said we're gonna use, we did our moles. So we have moles, there's X, Y, and Z. So we have our moles. Stoichiometric coefficients, we have those because that comes from this equation. And then pressure, we just solved this. N total, we solved it X plus Y plus Z. Okay. All right, so we can substitute in. So that's what you see here. Okay. Right here is the substitution. We have moles of hydrogen, right? Because that's in our products. But so the other tricky part is working with the stoichiometric equation and the actual equation, and when to use what. Okay. We have moles. So the moles is going to be the Y right here. Okay. So I don't have much room on this page, unfortunately, but let's set that up. So we have Y. And then you have the stoichiometric coefficient of the hydrogen, which comes from this equation. So that's to 1. Okay, and then you have oxygen. And we have Z. Okay, and that's raised to 0.5. Okay, it's because of that stoichiometric coefficient right there. And then reactants, from here we only have water. Okay, but you have moles of water. We have X. And stoichiometric coefficient is 1. Okay, and then you have pressure, which is this value, but I'm just going to leave it as P because I'm running out of room. And then you have N total, right? N total, that's X plus Y plus Z. And then this is all raised to that stoichiometric, change in stoichiometric. And that's just your products minus reactants. So you have, I ran out of room, but you have hydrogen and oxygen. So you have 1 plus 0.5. Oh, sorry. Yeah. It should be a plus. Okay. Yeah. Okay. It's here. I did it here, but not over here. So that should be a plus. Yeah. Your products minus your reactants of water. Okay. In their version right here, so you have, let's do the 1 plus 0.5 minus 1. Okay. But their version right here is because they put in for Y, they put in for Z, and they put it in terms of X. So in this equation right here that we set up, and this is where I would start with before going to this version of the equation, just because it's easier to follow, right? A lot of these problems will skip that step. But now you can put in for Y, you can put in for Z, and then the only thing you'll have in this equation here is X, because if you use this equation 1 right here, equation 2, and put those in, the only thing you'll have is an equation in terms of X. Okay. The last thing in the equation that they got was Kp, and that's from the table right in the back. So table A28, they said we're at 4,000 kPa. We go look for the row that says 4,000 kPa, look for our equation, which is there's the 5th column, and we get our, again, this is natural log of Kp from the table, and to get the actual Kp, right, we take the E of that, and so now we have the Kp, and we solve for X from this equation, which looks like a fun one, looks like probably iteration to get X, or you could try to do the math. I wouldn't. I would just try to iterate in this version. Some problems you don't have to iterate, sometimes you do, okay? But you get X, solve it. It's our only unknown in that equation, so it can be solved, but it's 0.222, okay? So that means, if we come back, that means X right there in front of the water is 0.222. So that means 70, the 1 minus it is how much of the water in the reactants went to hydrogen and oxygen. We're still left over with 0.22 of water at the end at 4,000 kPa, but the rest of it, 77.8%, went into hydrogen and oxygen. Any questions? All right. I also have a nice summary slide after this for, to apply these problems up on Canvas, but I'll go over it too. So Kp, so now this just kind of looks at the meaning behind the values you get. So Kp, this equilibrium constant, right, only back here, only depends upon temperature, okay, because temperature is the only thing in it. So no matter if you're at 1 atmosphere, 5 atmosphere, 3 atmosphere, 2, it only depends on temperature, okay? The other thing is, one is remembering how we got Kp is that if the back of the book has the reaction set up like this, and that's what it does, right? Is H2 breaking up into hydrogen and oxygen in table A28, and you set it up like this. If you set it up like this, the Kp actually changes, and it's 1 over Kp. Okay, so be very careful. Either set up your reaction exactly like what you have in table A28, or know the differences. Okay, and there's another difference in the next slide or two, and that's because it comes from the definition of Kp. That if you are setting it up in the opposite direction, these flip. The numerator flips to the denominator flips to the numerator in the Kp, which means it's 1 over Kp when you do that. All right. Kind of saw this in the example, but larger the Kp, because we saw a small Kp, the more complete the reaction. We saw a very small one like this. That means in this reaction, it's hydrogen into 2H, so low value of Kp. You're just going to be not get any H out of it. You're just going to be still at H2. In this equation, in this reaction, as the temperature goes up, we see the reaction is going more to completion. Right? Get up to 6,000 kPa. Now we're getting lots and lots of just H and not H2, right? Because the Kp went up. Pressure, right? We said this is Kp is just a function of temperature, right? So just a function of temperature. If we change pressure, Kp still stays the same. So this still stays the same, but we change pressure. That means everything else, like the composition right here, has to move around so Kp is still the same. So if we change pressure from 1 atmosphere to 10, Kp still stays, the left side of the equation still stays the same, but it changes your moles, okay? Things have to move around so that Kp is the same value. Okay? Inert gases. So if something's just along for the ride, like you have something in the reactants that's still in the products, but doesn't play a role in the reaction. So in this case, they're showing you have N2, and it's just along for the ride. It stays in the reactants, it's still in the products. It doesn't have any role in the actual reaction. The Kp stays the same, the equilibrium constant. But what will change in this is your total moles, okay? Because there's more moles right here than there was here. So that, even though Kp again is still the same for this reaction from H2 to H, the moles, total moles are different. So that changes, moves around again your moles, moves things around, even though Kp is the same value. Here's another example of understanding Kp. If your stoichiometric coefficients are double, Kp is squared. So again, if you set up your equation in the back of the book that's different than what they have, so if the back of the book shows something like this, and you set up your reaction instead like this, Kp is not the same value. Okay, it's squared. And that's because, again, comes from the definition of Kp, that if you double each of the stoichiometric coefficients from here, and that's what's happening from this equation to this one, they basically just doubled it. So multiplied times 2 to 2, you get this, which means your Kp is squared. So
they were cubed.
Well, you have to go through again and look at it. So 3, 3, 3.
Okay, so it just applies directly like that?
Yeah, it's just because this is 1 and this is 1/2 and this is 1, so you setting it up at 2. So, oh, you wanted this, you'd have to reverse calculate that. But
okay.
to calculate, what would KP if you now instead set it up as 3H2, right, plus whatever it is there, so 3/2. So, but if you did that, you'd have to, you know, go through, and that's what, then it changes what your KP is. So it's either set it up like you have an A28, or, you know, make sure you understand the repercussions of what you're doing when you change how your equation looks compared to what you see in the table in the back. Okay.
Okay, thank you.
Free electrons, I mean, we really won't see it in any examples I'll do or have for you, but they kind of just behave. I mean, they disassociate, and you'll see free electrons at very high temperatures, but we'll just treat them as a gas, a component in N total. Okay, so they'll just kind of be there. Okay, we'll just treat them like they're a gas part of it. The other big thing, which plays a large role in my research, equilibrium just provides actually when a reaction gets to equilibrium, when it balances, when the reactions at that temperature, reactants and products kind of balance each other out, and you get the equilibrium. It doesn't tell you how long that takes, is what I'm getting at. So this could take years, a reaction, okay? Equilibrium just says, oh, this is the composition you'll get when it reaches equilibrium. It doesn't tell you whether it's going to get there in, 0.1 seconds, 1 second, 10 seconds, 100, 10,000 seconds, whatever. It doesn't tell you how long that takes, which in my research matters a great deal, because I'm looking at engine combustion a lot, and that's a very short amount of time. Okay, so that's when you start getting into what's called kinetics, reaction kinetics, which brings in reaction rates as a function of, they have a time to them. So then you got to calculate things with time and how long the reactions had to get there. Okay, but equilibrium is still very useful and used a lot for different things because of that. It still can give a good approximation of what certain values would be. All right, so here's another example. Okay, it's a little longer one. It has 2 pages. Okay, as we have, in this case, we have a mixture. Okay, so we have 2 kilomoles of CO and 3 kilomoles of O2. Okay, and they're heated to 2600. So we have this, our main things, and then we have a pressure, another main given. They want the composition. So, and they tell us the products are just these 3 components. Okay, so our stoichiometric equation, we're going to pull the equation from the back that deals with, because we have CO, we have oxygen, they would go to CO2. Okay, so we're going to pull that equation. And that's our stoichiometric equation right there. So the stoichiometric equation again tells us stoichiometric coefficients, right? This is A plus B goes to C plus D, right? All right, now the actual. We have our CO and oxygen, and then we have the products is CO2, right? From CO and oxygen, but we're going to have some of the reactants left over, which is YCO, ZO2. Okay. All right, so we get our first equation is from our balance, from our carbon balance. Second, from our oxygen, and you see they did the same thing you saw in the last example. Is they set up the balances. They're just going through for carbon, oxygen, but then they put it in terms. They put Y in terms of X. They put Z in terms of X. Okay, just to get, and when you get to get that that equilibrium equation, to get everything in terms of X, so you're only left with one unknown. All right. So N total is your total number of moles is just X plus Y plus Z. Okay, so that's that. And then they again plugged in for Y, substituted for Z, and they got another term for N total as a function of just X. Pressure was given up here of 304 kPa. So again, 3 atmospheres. Okay. All right, so we have kind of everything now. Now it's just substituting into our equilibrium equation. Okay, let's do the general equation again. Okay, so that's the general equilibrium equation. We needed the moles of everything. So the moles come from the actual equation, right? So this is moles from actual. Stoichiometric come from the stoichiometric equations. Okay, so the moles we have in our, the other thing I should say is the setup of what's in the numerator and what's in the denominator, so A and B and C and D, that comes from just the stoichiometric equation also. Okay, so that's what's in the denominator and what's in the numerator. Okay, so there's a lot of mixing of understanding what's in the actual versus stoichiometric, and that's where the mistakes happen. Okay, all right, so we have A and B, right? And that is, if we come back, A and B, that was CO and oxygen. Okay, C and D, we only have one, so just C, say, but that's CO2. Okay, so that's where we don't have a D in this one. So we have CO2, and then we have our CO and oxygen. Okay, now we can substitute things in, understanding that. We have number of moles of CO, number of moles of O2, and then each of them to their stoichiometric, and then our product, CO2, number of moles, stoichiometric coefficient, and then the change in the stoichiometric products minus those reactants. Pressure and total. And again, they already solved for everything here, and now we, in terms of X, so they put everything in terms of X. Okay, even though we could go and have CO2 was X. Okay. CO2 stoichiometric coefficient was 1. And then we have CO, which is Y. And then we have Z for O2, but our coefficients, CO is 1, O2 is 1/2. Then we have pressure and total, which is X plus Y plus Z. And then the change in these stoichiometric coefficients, which was 1 minus 1 minus 1/2, I believe. Yeah. Okay, and again, they, like I said, they plugged in for Y, for Z. They put their equations from 1 and 2 for Y and Z. So then they just get left with an equation, one big equation with just X in it, the only unknown. Okay, so again, iteration to get X. And X is our actual moles of CO2, right? So then using the carbon balance and oxygen balance, you can get Y, or just using this equation right here, you can get Y and you can get Z, which is the moles for CO and the O2. Okay, so now you plug that back in, you have everything in the products in the actual moles for each, for that reaction. All right, so what's needed? So we could take that even further in a complicated reaction. Still, you want a minimum Gibbs equals 0. Okay, so if we generalize this, if we have a composition reaction that's occurring of CO2, CO2, and oxygen, we see there's two elements, carbon and oxygen, right? But there's four components. 1, 2, 3, 4. Okay, so that means if we do a carbon and oxygen balance, right, we're still going to be left with two unknowns. Okay, so that's what this is showing. You do 4 minus 2, you still have two unknowns. Well, for those two unknowns, we can actually set up two equilibrium equations to get those extra unknowns. Okay, all these examples before, we just did one. We just had one equilibrium equation, but we could actually do multiple within a general bigger equation. That's what this is showing, is if we had water and oxygen, right, they give you moles, 4,000, but we have all these components as what's left over, 4 of them. So you have water, you have your oxygen, but then you have hydrogen, you have OH. Okay, well, that's X, Y, Z, and W. So that's 4 unknowns, and you only have a hydrogen balance, which gives us 1 equation, oxygen balance gives us 2. Okay, so we still need 2 more equations, and that's where we could set up the equilibrium equations for what's going on in between these. Okay, so in this case, we're doing water with oxygen, so that's our first equilibrium equation. And then, basically they're picking equations from the back of the book that they have. So they have water, hydrogen, oxygen, water, hydrogen, OH. And both of those are in the back of the book, I believe. Yeah. And we're going to use equilibrium equations from each of those reactions. So that's our stoichiometric for each of those. All right, so at 4,000 kPa, they went and grabbed, or sorry, 4,000 Kelvin, they went and grabbed the equilibrium constant from the back of the book, and then they set up the equilibrium equation for each of those, reaction 1, reaction 2. Okay, for reaction 1, this tells us how to set it up. The moles just comes from, our X, Y, Z, and W. Okay, so that's where that comes from. The stoichiometric coefficients, again, come from the stoichiometric reaction. Okay, so plugging, N total is X, Y, Z, W. Plugging everything in. So in this one, they didn't substitute in because you can't get it in terms of just one unknown, because you have 4 equations, 4 unknowns, and there's no way to really get it simplified to 1 equation, 1 unknown without a really big headache. So you have 2 equilibrium equations here, but we have, so this is our equation 3, equation 4. So our unknowns are X, Y, Z, and W. We have 4 equations, 4 unknowns. You actually solve those simultaneously. Okay, so iteration, nonlinear regression solve or something to get there, and we get our values for X, Y, Z, and W. Okay, and then that tells us all our moles of what was left in our equation up here. Okay. Phase equilibrium, so this is with drying and force of magnitude on concentrations. Again, we won't end up getting to that, unfortunately. So that's chapter 16. We might be able to do one example. Let's do an example.